Testing on YouTube. All right, I think YouTube works. How's it going, Sagar Pillai or Payai? All right, and then the last one is X, which I think should be live shortly. Alrighty, perfect. And I think X is live as well. Let's make sure. I think it is. Okay, perfect. Let's go ahead and get this started. How's it going, Nikhil? All right, welcome to another Hoopo stream. We got a little bit of a weird one here for you guys today. This one's called Neural Network Diffusion. This is kind of a crazy concept. It's not fully fleshed out, you know. This isn't something that people are necessarily doing in production environments. You know, this certainly isn't being used in any of the AI demos or AI products that you guys are using nowadays, but it's a very, very cool idea. It's a very potentially powerful idea, and I just think it's an interesting wander through idea space. How's it going? Hello, phobic dude. Tim Stewart. T. Stewart. I tried to fix my microphone. Hopefully it's better, but let me know if it's not. How's it going, Ed? How's it going, Raphael? 2x speed, not working on YouTube. Yeah, you got to wait until the stream is over to 2x speed it, which I think is actually the best way to do YouTube. I actually do it for everything now, except for music. I don't listen to music on 2x speed, but pretty much everything else, 2x speed, and I feel like it's the only way to consume content. All right, so today's stream is going to mostly center around this paper here. This is a paper called Neural Network Diffusion. Came out 20th February 2024, so this week. And it's about using a diffusion model to generate neural networks. So most of you are familiar about diffusion models for image or video generation, right? So basically creating here this image of this cat by conditioning a diffusion model, usually a latent diffusion model, which is a diffusion model that operates in some latent space, which iteratively will remove noise until you get a sample from some distribution. In the case of image and video generation, the distribution of all images and video that you trained it with, right? But now, rather than generating images and video, we're going to be generating the neural network parameters. And here in this abstract, they say high-performing neural network parameters. I think that's a little bit maybe too grandiose, you know? As we'll see when we kind of go through this paper, this is still very early days, and they're not generating the model parameters for like a GPT-4, you know? They're generating the model parameters for very simple image classification models such as ResNet 18, which is a very old model at this point, on datasets such as CFAR 100, which is also a very old model. But the reason they're using these old models is because they're very small, and we'll see that kind of one of the current limitations of this approach is that it really only works for very small models. But that doesn't necessarily mean that there isn't a special use case where that could be still quite useful, and we'll look at that as well. So if we go into the abstract here, our approach is simple, utilizing an autoencoder and a standard latent diffusion model. So the autoencoder is going to be compressing these model parameters into some latent vector, and that latent vector in the latent space is what's actually going to be getting diffused by the diffusion model. So they're going to be doing a latent diffusion model. Our autoencoder extracts latent representations on a subset of trained network parameters. A diffusion model is then trained to synthesize these latent parameter representations from random noise. It then generates new representations that are passed through the autoencoder's decoder whose outputs are ready to use as new subsets of network parameters. Across various architectures and datasets, our diffusion process consistently generates models of comparable or improved performance over trained networks, with minimal additional cost. Notably, we empirically find that the generated models perform differently with the trained networks. Our results encourage more exploration and versatile use of diffusion models. So we're going to kind of skip to figure 2 in this paper to kind of explain exactly what's going on. And I think this figure is a pretty good summary of exactly what they're doing in this paper. So they're going to have to train an autoencoder, right? So an autoencoder is a combination of an encoder and a decoder, where the encoder will take something and compress it down into this little latent representation. You could think of it like compressing an image into a little vector of numbers. And then the decoder consumes that little vector of numbers and then outputs the full image, right? But in this case, it's not images. What you're going to be compressing is the parameters of a neural net, right? So basically a giant matrix of little numbers that represents the weights and the biases and maybe the batch norm layer, means and standard deviation, all the different little tiny parameters that you have in a neural net. And the encoder kind of crushes that into this tiny little latent representation. And then that little latent representation there, right, is used by the decoder to reconstruct the model parameters. And by using a reconstruction loss, where you basically want what's coming out of the decoder here to match what's going into the encoder there, you can get an encoder-decoder pair that are pretty good at compressing any kind of model parameter. So then, once you have this encoder and this decoder, you're going to have to train a actual diffusion model. This is the LDM here. This is the latent diffusion model. And the latent diffusion model will basically be able to start from random noise and iteratively remove the noise until you get to a latent representation that you could then feed into the encoder or feed into the decoder and get an actual image. So the diffusion model is what's actually doing the diffusion process here, and this encoder-decoder just basically compress these model weights into a latent. Once you've trained both of these, or I guess all 3 of these, the encoder, the decoder, and the LDM, which you're going to have to train separately, then you're going to be able to perform this inference pipeline. This inference pipeline is what you're actually going to use when you want to actually do something with this model. In this case, what you're going to be actually doing is creating model parameters for little tiny convnets and resnets that are basically pretty good at CFAR and MNIST, which is, again, kind of simple data sets, but this is more of kind of a proof of concept of an idea rather than necessarily some kind of like state-of-the-art production type of thing. So you can see here in inference mode, you start from random noise, you denoise it for however many steps using your latent diffusion model. You're going to end up with some latent representation. Feed that latent representation into your decoder here, which is frozen. I feel like they don't need to add the frozen here. In inference, it's already frozen anyways, but I guess just in case you wanted to know, the decoder doesn't change weights there. The LDM doesn't change weights either, so maybe they should have put the frozen symbol here on the LDM as well. But then once you get out of the decoder, you get these generated parameters, which you can evaluate and see whether they also have good accuracy. And kind of cutting to the chase here, the models that they are going to get out of that, the model parameters, are going to be comparable or improved performance. How's it going, Majetti? How's it going, Eleve Group? Okay. So in the introduction here, the origin of diffusion models can be traced back to non-equilibrium thermodynamics. So I guess this is the earliest diffusion model reference that they have here, 1997. And mostly these have been used for image generation and then now video generation. But video generation is kind of basically just image generation, if you really want to think of it that way. We demonstrate the surprising capability of diffusion models in generating high-performance model parameters, a task fundamentally distinct from traditional visual generation. Parameter generation focuses on creating neural network parameters that can perform well on given tasks. And this is kind of not been well explored yet, as they kind of keep mentioning over and over again. And it's weird, right? It's a weird thing to think about, where you can imagine how you could use a diffusion model to remove noise from images. You can imagine how there's some distribution of all possible images, and that distribution you could eventually learn it with a diffusion model, but it's a little bit more weird and more abstract to think of the fact that there's some distribution of model parameters and you could get a diffusion model to basically learn that distribution of model parameters. It's kind of a weird thing to think about, but it actually does work, right? So this whole paper is basically proving the point, although just with kind of like didactic examples, but it's proving that, yes, this does work. And maybe this is the way that we'll be doing stuff in the future, right? Maybe in the future, rather than training models from scratch with gradient descent, which is what we do now, right? We basically use the slope and gradient, calculate the gradient, push that, adjust the weights a little bit. Get a new gradient, adjust the weights a little bit. Put another mini batch in, get the gradient, adjust the weights a little bit, right? And we take millions and millions and millions of these little tiny training steps where you're basically moving through this loss landscape until you find a little local minima, which hopefully is a global minima, and that represents basically a trained neural net. But in this case, if you can just train a diffusion model to give you the final answer, right, the final trained model, then you don't need to do this complicated training process that's going to take forever, right? So maybe this is like a cheat code, right? Imagine if you could just generate a neural net in one shot or in a couple shots, right? Because you're going to have to iteratively denoise a little bit. But that would be orders of magnitude faster than this kind of more brute force kind of search process that we're doing right now, where we're using SGD to kind of get to the final answer. So both neural network training and the reverse process of diffusion models can be regarded as transitions from random noise to specific distributions. In this case, either the distributions of images or the distribution of neural network parameters. High-quality images and high-performing parameters can also be degraded into simple distributions, such as Gaussian distribution through multiple noise addition. So if you can take the model parameters and just add random noise until you eventually get pure noise, that's kind of similar to images, where you can just take an image and just add random noise until you get pure noise, right? So that's kind of the analogy there, is that, hey, neural network parameters, hey, we can put it in a two-dimensional matrix and it kind of looks like an image, and then what do we just kind of pretend that it's an image, I guess. I wonder how this would work with large world models and ring attention. So I would say ring attention and large world models are more about the context length of transformers, which is kind of the efficiency of a neural network, right? Trying to get more input that you can use inside a transformer architect. This is almost more of a completely different branch, right? This is like going all the way down to the bottom of the tree of machine learning and saying, hey, everything that we're doing right now is based on this SGD, right? Gradient descent. And that's all the techniques that we have right now. What if we go all the way back down to this like root node where we decided that SGD is the way to do everything, and instead try a different approach where now we're basically diffusing the actual final parameters. So neural network diffusion, they're going to call this PDiff, where P stands for parameter and diff stands for diffusion. So that's the name that they chose. The diffusion model has the capability to transform a given random distribution to a specific one. The random distribution is the Gaussian noise. Our method is simple, comprising of the autoencoder and a standard latent diffusion model. First, for a subset of parameters, the model is trained by the SGD optimizer. The autoencoder is trained to extract the latent representations of these parameters. And then we leverage a standard latent diffusion model to synthesize latent representations from random noise, which is basically this figure that I showed you. But the tricky part here, right, is this first part here, where they're going to say that we need a subset of parameter models trained by SGD. So unfortunately, one of the more annoying realities of this type of work is that if you're going to train a diffusion model to basically start to learn this distribution of model parameters, you're going to need a huge data set of model parameters, right? And that's the hard part, right? Where we can get massive data sets of images, right? Because we have so many cameras and there's so many images on the internet, so you can get a huge data set of images. But getting a huge data set of model parameters, of like, hey, here's a set of model parameters that represent a fully trained model, that's much more difficult for a variety of reasons. And one of the reasons is there's just less of them, right? The other reason is that there's a lot more kind of weird stuff in the model parameter space, right? In image space, it's actually quite consistent, right? Images are 3-channel, usually R, G, and B. There is different width and heights. You can have different images that are different width and heights, but you can just crop them, and it's totally fine, right? Images are much more kind of consistent. The image space is more consistent, and there's certainly a lot more samples from that image distribution than model parameter space, right? Model parameter space, the model parameter space of a ResNet 18 is completely different from the parameters of a GPT-4, right? It's not the same, the different dimensionalities, different numbers of them. Some of them you don't even have. So it's a much more difficult problem. Kind of runny nose right now. How's it going, 2ARX? Got myself some coffee here. Got myself some agua. Okay. But ultimately, they're going to be, oh, look at that little typo here, neural network diffusion. Somebody should open a GitHub issue to tell them that they have a typo in their paper. It achieves similar or even enhanced performance. Our generated models have great differences from the trained models, which illustrates our approach can synthesize new parameters instead of memorizing the training samples. And what they wanted to say here with that sentence is that it's not that when you have such a small training data set, which they have, right? It's not necessarily super small, but compared to the image training data sets that people use for image diffusion models, the model parameter data set that they're using here is really, really small. So whenever you have a really, really small data set like that, you can run into an issue known as overfitting. Overfitting is when you basically kind of memorize. So they wanted to make sure that they're not just training a diffusion model that just basically memorized the 4 training models that they had and then just basically spits out some variant of those exact 4 models, right? They want something that is finding new, novel points in model parameter space that have a good test accuracy. Okay, so the next thing they're going to do here is they're going to go into a kind of preliminary on what a diffusion model is, and we are going to go into that, but before we go into that, I kind of want to show that this isn't necessarily entirely new, right? So I have another paper pulled up here. This is a paper released on the 26th of September 2022, so a little bit older. This one's called Learning to Learn with Generative Models of Neural Network Checkpoints. And believe it or not, this William Peebles here, this is the same guy that did the Sora. So the Sora video diffusion model that OpenAI released, we did a stream on that last week. And basically one of the main people behind that was this guy called William Peebles or Bill Peebles. And just to show you that it's kind of a small world, here he is in another paper the week after the week we did the Sora stream. And it's kind of the same. This is a diffusion paper as well, but I don't know, I just thought that was kind of cool that the same guy that's behind the state-of-the-art Sora diffusion model is the guy who was just a couple years ago publishing papers on basically this diffusion in model parameter space. But this paper has some pretty awesome figures, so I figured we should look at it. How's it going, Aries? Aurélien? We explore a data-driven approach for learning to optimize neural networks. We construct a data set of neural network checkpoints. Checkpoints is basically like whenever you're training a neural network with gradient descent, right? You're basically pushing these little gradients and adjusting the parameters of that model. And you're going to push millions of gradients, right? You're going to take millions of these little training steps where you're going to be modifying all the different parameters. And ultimately, you want the specific set of model parameters that gives you the highest test accuracy, right? So as you're training, you're going to be constantly checking your model's test accuracy, not at every single training iteration, but maybe every 100 training iterations or 1,000 training iterations. You'll take what you currently have, see how it performs, and if it performs better than what you had before, you might save a checkpoint, right? And this checkpoint is basically, here's where the neural network is at, here's all the parameters, here's maybe the loss that was achieved at this particular time, here's maybe, if you're doing reinforcement learning, here's the reward that this model achieved at this particular time, and so on, right? And if you train a neural net for a lot of training steps, you're going to end up with a bunch of these checkpoints. And in this data set, or in this paper, they're basically going to say, okay, we're going to have a bunch of those checkpoints and pretend that they're basically a data set. So we're going to have a data set where we have these checkpoints that represent the weights of a neural net, and then also the kind of loss that you got at that specific checkpoint. And they're going to train a generative model. In particular, the model is a conditional diffusion transformer that, given an initial input parameter vector and a prompted loss, error, or return, predicts the distribution over parameter updates that achieve the desired metric. So this one's going to be a little bit different, right? This first paper here, the kind of the coolest part of this paper, which is the more recent one, is that this is a latent diffusion model, right? Where basically the diffusion process is happening in this latent space, which is a compressed form of the model parameter space. This one here, which is an older paper, William Peebles' paper, the cool part about this one is that it's a conditional diffusion model, right? So the diffusion model isn't just kind of just generating random images, right? Or random model parameters. What it's actually doing is you can condition it. And in this case, they're going to be conditioning it on the loss, right? So let's actually look at what that looks like. So this is what the data set of neural network checkpoints look like, right? So each checkpoint, which is one row here, you're going to have a set of model parameters, this theta 0, and then you're going to have like the loss that you actually got at that, right? The actual, maybe the test eval accuracy, or in this case, I think it's like the actual just pure training loss. So that you can then train this diffusion model, which in this case, it's not a latent diffusion model. In this case, it's actually diffusing directly in the model parameter space, which is a little bit outdated, right? Most diffusion models now, they operate in latent spaces. So seeing a diffusion model that just operates in the raw model space is kind of like seeing a diffusion model that operates in the raw image space, right? It's kind of, you don't really see that nowadays, but this is also kind of proof of concept, small little models. But then you'll be able to say, okay, prompted loss. So the same way that you prompt stable diffusion with a piece of text, and then the generation of that image is basically conditioned on that piece of text. Here, you're going to be prompting this diffusion model with a specific loss. So you're going to say, okay, I want a loss of 0.01. I'm going to feed that loss of 0.01. I'm going to feed some starting theta, which can be basically noise, and then it'll give me new theta, where theta is the model parameters, that should in some way kind of have this loss, right? It's not going to be perfect, but they do actually end up showing that you can actually do this, and it kind of works, with the caveat that this is only really being done for simple data sets. But this is a pretty awesome idea as well, right? The idea of a conditional diffusion model where the condition is not just kind of text tokens, it's basically specific losses or specific rewards if you're doing a reinforcement learning type process. So they call this G.pt. This is a little pun on words. .pt is the usually the file extension that you'll see for checkpoints. So if you're training with PyTorch, whenever PyTorch saves the model to a file on your computer, it'll save it as a .pt file sometimes. So they're kind of playing a little pun here that GPT, it's a generative model, but it's generating checkpoints, so they're calling it G.pt, right? So that's the joke.jpg. Tim Brooks also works on Sora. Maybe, I forget. Maybe it's just because Will Peebles has just such a great name. Just full caveat, I don't actually know these people. I don't actually know Will Peebles and Tim Brooks, but Peebles is just such a memorable name that Tim Brooks is a very forgettable name. So it could be the case. I think you might be right, Ed, that Tim Brooks has also worked on Sora. I just kind of forgot because it's just a very generic name. It's like John Brown, or some kind of name like that. It's very hard to remember, but the Peebles is just such a badass name that I feel like I just instantly see it now. Okay. I liked the beginning of this paper because I thought it was a nice little summary of exactly what's going on. So gradient-based optimization is the fuel of modern deep learning. Techniques of this class, such as SGD and ADAM, are easy to implement, scale reasonably well, and converge to surprisingly good solution, even in a high-dimensional non-convex neural network loss landscape. So what the fuck is going on here, right? Is high-dimensional non-convex neural network loss landscapes. What they're saying is that you could think of the gradient descent process, right, of which SGD and ADAM are, as basically you're moving along this space. Let's actually do this atom momentum. I've shown this a million times before, but I think it's very indicative. Yeah, this thing here. So this is like a little GIF that shows you what's going on. Let me see if I can find it. No. Okay. Oh, yeah, here we go. So you can think about this like this surface here as basically the loss landscape, and areas where this surface is close to basically lower means that the loss is lower. It means that what you're doing with SGD is you're moving around, and every single training step is like basically just moving a little bit in this space, right? And it's kind of still like part of the black box nature of neural nets is that SGD working in this high dimensional non-convex loss landscape is still kind of like a mystery, right? The fact that we can even get and converge to surprisingly good solutions or find a specific set of model parameters that works well, and we get to that by just kind of like taking little steps in model parameter space, that's kind of magic to begin with, right? And that gradient-based optimization is like the very bottom of the tree of pretty much all deep learning that we use right now, right? That, hey, let's make a giant over-parameterized model, and we'll just start feeding it batches of data, use those to kind of push little gradients and change these weights over time and eventually get to a good solution, right? And the fact that we get to that good solution is still kind of like not fully understood, right? Like why is there specific good solutions inside these giantly over-parameterized models that work well for the things that we want to do? These manual optimization techniques, I guess is what they're calling them, have led to large advances, but they suffer from an important limitation. They are unable to improve from past experience. So what they're referring to here is actually generally known as the problem of meta-learning. So meta-learning is another way to say learning to learn. So, hey, wouldn't it be great if we could figure out a way to more quickly learn things? So can we learn how to learn things, right? So this meta-learning, there's some famous people in the field now, such as Chelsea Finn, who are very known for that in reinforcement learning, but people have been doing this as early as Schmid-Huber here. So for those of you that are Schmid-Huber fanboys, here's the properly attributed 1987 Schmid-Huber reference for meta-learning. I'm sure he'd be very proud about that one. But we want learned optimizers that are capable of leveraging their past experience, right? If only we could have some type of, if only we could teach gradient descent to get smarter every time we train a neural net, but it doesn't, right? It's like every time we train a neural net, we have to basically do the same SGD that we do every single time, where it's just kind of like taking these little steps in model parameter space, and we're burning massive amounts of GPUs to get to that final answer. Taking a modern deep learning perspective suggests a simple, scalable, and data-driven approach to this problem. Our community has trained a massive number of checkpoints. These checkpoints contain a wealth of information, such as diverse parameter configurations, rich metrics such as test losses, classification errors, and reinforcement learning returns that describe the quality of the checkpoint. They probably meant training losses and then test accuracies. I think that's the terminology that they use for the rest of the paper here. So the loss might be the training loss, and then the error is like the error that you get when you actually evaluate that model on the test data set. Or maybe it's test losses, I don't know. The test versus train there is like, what data set are you evaluating it on? Are you evaluating it on the test data set, which is held out, which means you're not actually using it when you're doing SGD, or are you doing it on the training data set, which is what you're actually sampling mini batches of and pushing gradients of? Given an initial input parameter vector, these models are trained to predict the distribution over updated parameter vectors from a single network architecture that achieves the target metric, right? So they're conditioned on a specific metric, and then they try to basically generate the set of model parameters theta that would produce that specific metric. It is able to rapidly train neural networks from unseen initializations with just one parameter update, and it can optimize non-differentiable objectives such as RL returns or classification errors. So this last line is important, right? Because the whole reason that SGD works is because you can take the gradient of the model with respect to some input, right? So you can basically feed a neural network some input, get some output, and then say, okay, this is the output that it produced. I'm going to create a loss, such as a classification loss or some kind of MSE, or like there's a billion different types of losses, but that loss, I can then say, okay, well, this is the output I had, this is the output I wanted, what's the difference between those? And because every single part of my neural network is differentiable, I can then push a gradient all the way back, right? I use this chain rule from calculus where I say the derivative of this with respect to this, with respect to this, with respect to this, and you can kind of just infinitely keep going all the way back and update the parameters of your entire model. But if you move to this paradigm here, where you're basically now just generating pure model parameters, it doesn't need to be differentiable. And I think that that's important because it means that we're going to, it also opens up model parameter space, right? Because right now, all the neural network architectures that we have to be differentiable in order for us to push gradients into them, because the way that we're finding this final answer is through SGD. But if we get to a point where we basically just generatively create these model parameters themselves, we don't need those model parameters to be part of an architecture that is differentiable. You could just have a non-differentiable architecture that would be impossible to push gradients into, but it doesn't matter because you're basically just predicting the entire final model parameter directly. So that's kind of like an important little point to say there, and why this is such a promising potential area to look into. Okay, so that's the other paper here. I do want to point out one thing that they show here just to kind of motivate what's going on, right? So here's the optimization curves for here CartPoll, MNIST, and CFAR. So I have some of these pulled up. MNIST is this. This is a data set. This is Jan LeCun's original baby. So basically Jan LeCun created this very simple classification problem where you're basically trying to classify these images of handwritten digits. Some of these might actually literally be written by Jan LeCun. So some of these might actually be Jan LeCun's handwriting. I'm not entirely sure if it is. Maybe he got it from somewhere else, but I wouldn't be surprised if he actually wrote a bunch of the MNIST digits, which is kind of cool to think about. But it's a very small data set, right? It's a very old data set. It's a 20 by 20 pixel box, 28 by 28. These aren't even 3-channel images. They're 1-channel images. And it's a classification problem with basically 10 classes, which is extremely small. CFAR 100 is a little bit better, but it's still quite old, right? Look at these 32 by 32 images, and there's only 100 classes, right? Which are things like bird, deer, dog, frog, horse, and so on. So very simple kind of problems. But the reason people use these simple problems is because you can experiment very quickly, right? So every single one of these training runs doesn't take very long because these problems are very simple. So CartPoll is basically the same type of idea. It's like the MNIST for reinforcement learning. CartPoll is basically you're balancing this pole on a cart like this, and you control basically the XY movement of the cart, and you want to balance the pole. So it's like the simplest possible reinforcement learning environment. So here what they're showing you is the standard training curve for MNIST or CFAR, right? So basically you can see here this noisy step through model parameter space as you're going cruising through that loss landscape. You know, you're just taking little steps, and over time you can see that your loss goes lower and lower and lower and lower, right? But that takes forever, right? Think about that. That's 12,000 steps that you had to sit there and wait for your GPU to take these little steps in model parameter space on this loss landscape. But this red line represents this diffusion model, right? And that's the magic, is that, hey, if you can just immediately, through a couple steps of denoising, just get to the final answer, look at how much compute you just saved yourself, right? That's absolutely massive, right? So that's the promise of these type of techniques. All right, let me pause here, see if anybody has some questions. Hashtag Dr. Peebles. Yeah, I think we need to have that somewhere. I heard meow in some videos. Is that your mentor? Yeah, I do have a cat. So there's a cat known as Boo or Babu that is a white Bengal cat. That's the cat that appears in the thumbnails. She usually doesn't hang out here anymore because I think she got scared by the giant didgeridoo, but occasionally she makes appearances. Okay, so let's go back to the original paper here, and maybe we'll go into here. So our neural network diffusion, a little preliminary on diffusion models. How do diffusion models work? So diffusion models basically have some sample, x naught, sampled from Q of x. So Q of x is the distribution that you want to match, right? That's the magical distribution. In the case of images, it's basically the distribution of all images. So all valid images are basically can be represented by some distribution in the space of all possible images, right? And there exists an equivalent kind of distribution for all possible neural network parameters that are valid and give high accuracy. So ultimately what we're really trying to do is basically get this Q of x. If only we could have that little Q of x, then we could just basically sample from it, and every sample from it would be a valid image, and every single sample from it would be a valid neural network parameter. But we don't have that actual distribution in some form that we can just plug in some number and get something out, right? We only have samples from that distribution. So in a diffusion model, you're going to be sampling those. That's going to be your images or your parameters. You're going to be adding Gaussian noise for t steps. Usually this is something like 10 steps, although people have gotten it down to basically just one step, and I've seen it as high as like 1,000 steps. But any kind of diffusion model is removing noise over a series of steps. It starts from pure noise. So you see here, this is a normal distribution. This is pure noise here. The scheduling of the noise, so the amount of noise that is being added during this forward process has usually a schedule. The schedule means that kind of usually towards the end here, maybe you'll add more noise, and towards the beginning here, maybe you add less noise. So the amount of noise changes depending on where you are in this diffusion process. Different from the forward process, the reverse process aims to train a denoising network to recursively remove the noise. It moves backwards on the multi-step chain. So here you're basically trying to remove the noise. So given the x of t, you basically try to get x of t minus 1 by predicting that noise and then removing it. The thing that is actually predicting the noise is this denoising neural network parameterized by theta. So that's the actual LDM, right? This LDM is a little neural network that has a bunch of parameters, which we're representing with the variable theta. And we are trying to find those thetas, right? So ultimately, when we're training a diffusion model, what we're doing is we're trying to find these parameters theta for that denoising network that basically knows how to remove the noise by, it can either predict the noise or it can predict the signal too. But the denoising network in the reverse process is optimized by the standard negative log likelihood. In this case here, they have a KL divergence loss. This is a very common metric that basically tells you how similar this thing is here to this thing here. So basically you can see that the KL divergence is between this P of theta, which is generating xt minus 1 given xt, and you want to basically have that distribution match this Q distribution, right? Where the Q distribution is this magical distribution that we were talking about before, this Q of x, which is either our image distribution or our model parameter distribution. Okay. So that's diffusion models. Given a set of trained high-performing models, we first select a subset of these parameters and flatten them into one-dimensional vectors. Subsequently, we introduce an encoder to extract the latent representations, accompanied by a decoder responsible for reconstructing the parameters from the latent representation. So they're talking about basically this step right here, right? First things first, this is a latent diffusion model, so you're going to have to train an encoder and the decoder. So you're going to start with a data set of basically fully trained neural network model parameters. They're calling these high-performing models. I feel like the high-performing, again, is like a little bit cheesy, you know, like we're talking about like a 2-layer MLP that does like MNIST. So what does that really mean? Is that really a high-performing model? Okay. Preparing the data for training the autoencoder. We default to synthesizing a subset of model parameters. To collect the training data for the autoencoder, we train a model from scratch and densely save checkpoints in the last epoch. So the last epochs are basically how many times you go through your training data set. So epoch 1, 2, 3, 4, 5, right? 5 epochs means you've gone through the full MNIST data set 5 times, right? So what they're saying here is that they're going to train this model from scratch, the model that is the input parameters here, and then the very last epoch, they're basically going to save checkpoints for all the batches of data that they feed. That's what they mean by densely saving checkpoints in the last epoch. It's worth noting that we only update the selected subset of parameters via SGD and fix the remaining parameters of the model. So this was another kind of letdown for this paper, unfortunately. They don't do the full model. They actually just do a subset of them. So the input parameters here aren't even all the parameters of the neural net. What they are is basically a subset of the parameters, usually just the very last parameters. So for those of you that have maybe been around a little bit longer, most of what we used to do 5-10 years ago was basically you would take a pre-trained model such as a ResNet and you would fine-tune it on your specific data set. But when you were fine-tuning it, you usually wouldn't push gradients all the way to the bottom, right? You would only really retrain the head of that model, right? So the last couple layers is really what you wanted to get as the result of your fine-tuning process. Everything else is frozen underneath. So they're doing something a little bit similar here where they're only going to be generating the last couple layers of these models, which is a little unfortunate, right? I feel like it would have been way cooler if they generated the entire model. And they do have some examples of that, but if you generate the whole model, you're going to have to generate a much smaller model. My nose is running today. Jan was flaming everyone when Sora dropped and then Facebook released the Aria dataset. Yeah, I think Jan LeCun just likes arguing, man. You can't, you know what I'm saying? That guy just loves Twitter. He just lives on Twitter and he loves arguing with people on Twitter. But that's his job. You know, his job is just to argue with people and be a kind of a thought leader, I guess. All right. We flattened these parameters S, which are basically just a bunch of model parameters, into a one-dimensional vector V, where D is the size of the subset of the parameters. So they're basically taking all these model parameters and just flattening them into this little vector, which is basically what they do in the Peebles paper as well. So here in the Peebles paper, let's see if I can find the relevant figure. Is it this one? No, I think we're going to have to look at a different paper. But, okay, so here we go. So you see how here you have a little neural net, and then you're flattening it into this one-dimensional vector of weights and biases that basically represents the weights and biases of this neural net, right? So that's what they mean by flattening. We'll go back to that paper. I just wanted to show you guys that figure. Okay, so to train this autoencoder, they're going to have basically these flattened model parameters, and they're going to be adding random noise, feeding it into the encoder. So here you have your encoder. You're feeding in your model parameters. You see this little chi here, this fancy script E. This is noise. So EV and EZ denote random noise that are added into the input parameters V and and latent representation Z. So they're adding a little bit of noise here and they're adding a little bit of noise here, right? It's kind of like a form of augmentation. You have such a small data set that training an encoder and a decoder on a very small data set is not a good idea. So one way to kind of make your data set less small is to basically say, okay, well, let's add just like a very little amount of random noise to this model, and now it represents a slightly different model, right? And let's add a little bit of random noise into this latent representation. So that's what's going on here with this chi V, chi Z. The decoder here takes your latent Z, which is what's outputted from your encoder. So your encoder is consuming your flattened model here, V, outputting some Z. Your decoder is consuming the Z, which is the latent, adding a little bit of noise and outputting this V prime. And now you have this V prime, you have this V, and you're going to basically do a pretty standard reconstruction loss. In this case, your good old-fashioned mean squared error, MSE, between V and V prime. Here's your VK minus VK prime, the difference between those squared, and that's your reconstruction loss that you're going to be using to train your encoder and your decoder. Okay. How's it going, Amelie? So, now that we're in the parameter generation part, the memory cost of this operation is too heavy, especially when the dimension of V is ultra large. So, what they're saying is that these one-dimensional vectors V, which is the flattened model parameter, so they took all the parameters of this ResNet 18 model, flattened it into this one giant vector, and then that's what they're trying to compress into these latents, right? But that doesn't work if you have, or that works if your one-dimensional vector V is maybe just the parameters of some multi-layer perceptron, right? You could fit that in a one-dimensional vector that's reasonable. But imagine trying to do this with something like a GPT-4 where you have billions of parameters, right? And it would just be too big, right? You can't train an encoder decoder for something that the initial representation is absolutely ginormous. I think you could, but you don't have that type of budget when you're just like some random researcher here, right? So that seems to be something that pops up time and time again in these papers, and that also happens in this one here, right? Where basically this theta here, this needs to be kind of small. So in this paper, they kind of, let me see if I can find the exact part here. But the models that they generate in this are very small, right? So they're generating very small models in the Peebles paper. It's just a couple layers in a multi-layer perceptron, and this one as well. Let me see if I can find the exact thing here. Yeah, we default to training ResNet 18. So ResNet 18s are very small, and let me show you guys a little ResNet. So this is a pretty awesome visualization I found. This is similar to the other visualizations I've shown. This is a ResNet 50. So the ResNet 50 has 50 layers. So if you were to actually count all these little layers here, there would be 50 of them. And this is it's like a cool visualization where you can see each of the individual little neurons in each of these, right? Pretty badass little visualizer. So you can actually see, you can go all the way to the beginning of the network here, and here's the input image. Ooh, I'm like very bad at these, but look at that. You got your 3 channels, your RGB, but this is a ResNet 50, right? Which itself is pretty old, right? There's way more modern things of that. And they're not even doing a ResNet 50, they're doing a ResNet 18. So ResNet 18 is like a small version of a ResNet 50, which is already old. And they do this on a VIT Tiny and a ComNext. These are more modern architectures, but they don't generate the full models. They only generate the last 2 basically layers, which is a little bit of like a letdown, right? So ultimately, the problem with generating model parameters directly is that model parameters can be very, very high dimensional, billions of possible model parameters. So generating that directly is very expensive. So even in this one, where they're basically training this encoder decoder to compress it down to a smaller latent and then generate that latent instead of the giant thing, they're still limited to either just the last 2 layers of a VIT Tiny or a small little ResNet 18. Okay. Now let's go back up here. Or actually, no, this is a good time to think about, does this mean that this is doomed, right? If we're kind of stuck right now because these kind of model diffusions or neural network diffusion research papers, right, both this one and the Peebles one, they both run into this issue that you can't generate something that has 4 billion numbers or 7 billion numbers, right? You're generating these little tiny ResNets. Does that have any use to us? And I think that's where I'm going to introduce this paper here, which I briefly showed. This is a paper that came out in 29th of March 2023, Hyperdiffusion, Generating Implicit Neural Fields with Weight Space Diffusion. So an implicit neural field is basically a way of describing a nerf, right? If you guys have done anything in the 3D world, you might have heard of nerfs, which are not as popular now as they used to be, right? Gaussian splats have become a little bit more popular, but nerfs are basically little tiny multi-layer perceptrons that they're a field, right? They're supposed to represent a field. A field is basically a function that you can evaluate at any point in space. In this case, what that little neural network is trying to represent is the surface of an object, right? So they're basically trying to represent this function, which is telling you how far away you are from the surface of an object. But why is that important? The reason it's important is because nerfs are tiny, right? Nerfs, or implicit neural fields, they're just these tiny little multi-layer perceptrons. So now that's a much better application for weight space diffusion, which is just another way of weight space diffusion is diffusion in the model parameter space or the weight space, right? It's the same thing as neural network diffusion, or in this one here, they call it generative model of neural network checkpoint. All of those are referring to the same idea, which is the idea of using a diffusion model to generate model parameters, right? But in this case, it kind of feels pointless because you're just generating the model parameters for these tiny little classification models that work on these toy data sets, which is like, what the fuck is the point of that, right? But here you're like, oh, wait a second. NeRFs are actually very small. So if we're only capable of generating very small little models, why don't we generate NeRFs? Because they're pretty small and we can actually use them for things. So in this paper, they basically do the same thing. This is a diffusion model in the pure model parameter space. So this is not a latent diffusion model, but what they're generating is basically NeRFs, and they can generate NeRFs that represent different objects, right? So you can imagine training a NeRF on a bunch of different objects. You have one NeRF per object. So each one of these objects is trained from a data set of multiple views of that object, right? And then you're training a NeRF to generate that. And then you have a data set now of here's a little NeRF, a little MLP, and then here's the output that it produces. Here's the NeRF, here's the output, here's the NeRF, here's the output. You basically train your diffusion model to then generate NeRFs that produce something, right? So you could condition this on the name of this object or the class of this object, and then condition that diffusion model such that you give it the name of that object or the name of a new object, and it'll generate for you a little multi-layer perceptron that you can then use as a NeRF to generate the surface of the object or the mesh of the object, right? And this is an idea that we've seen before. So here's another paper. We went over this one in a stream. This is Shape E, generating conditional 3D implicit functions. So 3D implicit functions, conditional 3D implicit functions. This is also NeRFs. So this is an OpenAI paper that came out in 2023. And in this paper, they did something really cool, which is they generated the parameters of an MLP or a little NeRF directly. So they basically feed a point cloud and some learned embedding. I don't know, this is probably the class. And then you can see here that what actually comes out of the neural net is the weights of a little multi-layer perceptron. So here they're kind of generating it directly with a transformer, but here they're doing it with a diffusion model. But both of these papers, I think the important thing to realize from these is that they're generating the weights of a NeRF because the NeRF is very small to begin with. And that's kind of the secret, is that you can, even small NeRFs are good. And here's a kind of an interesting figure here. Denoising the MLP parameters, aka the NeRF, at various time steps, visualize with their corresponding shapes from random noise to fully denoise. So if you were to take your diffusion model, which you have trained to generate the parameters of a multi-layer perceptron, which parameterize implicit neural field, which parameterizes, or which is modeling an object, right? What happens if you look at the weights of that little multi-layer perceptron that represent that NeRF over the course of the denoising process, right? So here, right, you're removing the noise from the parameters of a neural net, and you can see here they give you the accuracy, right? So in this one, they're generating the parameters of a classification model, so they can say, okay, at the beginning, it has a classification accuracy at 1.4, which is basically garbage. But then as we slowly remove the noise, we can see that the accuracy of the model goes up, which means that your little ResNet 18 that you're generating is getting smarter and smarter and smarter, better and better at this classification, which is measured via accuracy. But this one here is a little bit easier to visualize because this little MLP is going to be used to create this object, right? So you can just look at, okay, well, if we were to take it at the very beginning and see what kind of object it produces, you can see it in a much more visual kind of 3D and kind of like pleasing way, how over the course of this diffusion process, it gets better and better at becoming this NeRF that you want it to become. The iterative application of the denoising operator eventually converges to a quality output shape. Pretty cool little stuff there, right? So, I mean, this grain of salt, right? Because also, like, NeRFs are kind of dying. You know, some people might be triggered by that. I think there's some NeRF fanboys who still want to hold on. Same way that there's some ConvNet fanboys, you know, like I would say Vision Transformers beat the ConvNets and Gaussian splats beat the NeRFs, but there's still people who believe in the NeRF supremacy. There's still people who believe in ConvNet supremacy. So maybe we will be generating all of our 3D objects in the metaverse using a diffusion model that generates the weights of a multi-layer perceptron, which are a NeRF. You know, maybe that's where it all ends up. Okay, I'm actually sweating, so I'm going to remove the hoodie, even if it makes me appear uncool. I appreciate the compliment. I always have the best sites and reference apps. I didn't make any of these, so it's like, it's not like I made this, right? I just like found it just through search. The only thing I would do differently with this one is that it's like a little bit too like long, right? It's like I feel like they could have done it a little bit more like compressed, you know, like it's like kind of awkward to like manhandle this thing. Okay, we're going back to this paper. Where were we at? We were here. We were looking at the autoencoder. We were looking at the generation. The generation kind of is limited by the total number of parameters, right? So you're kind of only generating very small neural networks. So those very small neural networks have to be for either classification on these tiny data sets, or maybe it's just the last couple layers of a VIT, or it's just a NERF because a NERF is pretty small to begin with. Okay. So maybe some more details on what exactly their models look like. So the autoencoder and latent diffusion model both include a 4-layer one-dimensional convnet, which is kind of shit. I'm just going to go out and say this, right? So what they're saying is that their encoder-decoder is basically just this tiny-ass one-dimensional convnet. So that's not good. You know, that you're not only are you like encoding something which is already kind of toy, which is a ResNet 18, but now you're also encoding it with a very, very small encoder-decoder. Like, what are we doing? And it's also the latent diffusion model is also a one-dimensional convnet. You know, that's not necessarily great. At least in Peebles' paper here, the diffusion model that they use is a transformer. So this is actually quite modern. You know, for a 2022 paper, the diffusion model, usually it's something like a UNet, right, which is a convnet, or here in this 2024 paper, they're using a one-dimensional convnet. But in this 2022 paper, Peebles is using a transformer to basically diffuse, and not even in the latent space, it's diffusing directly in the model parameter space, where the model parameter space is basically taking all the layers, let's actually read the description here. The task level network F theta will contain many unique layers, each with potentially different number of parameters, right? So the task level network is like the ResNet 18 or the NERF. We define the ith token as the flattened parameter vector of the ith layer. So they basically take all the parameters of this ResNet 18, or I think in this one they are generating little multi-layer perceptrons, and then they flatten all those parameters into just this one vector, and then they cut it. And layers with multiple groups are decomposed into separate tokens. These tokens will be of different dimensionality, which is kind of sketch. They do project them each into a vector representation. So kind of they have to add this extra step here that projects such that these tokens are all the same dimensionality so that you can consume them with a transformer. So it's kind of reminiscent of a lot of the tokenization type of stuff that we're seeing now, right? It seems like ever since Karpathy released that tokenization video, everybody's kind of obsessed with tokenization. Are we tokenizing images correctly? Are we tokenizing audio correctly? Are we tokenizing text correctly? And here, this paper kind of makes you think about, hey, if we're going to be generating the parameters of a neural net, how do we tokenize that, right? How do we tokenize the layers of a neural net? And this is a pretty naive kind of a way to do it. You basically just, okay, take all the parameters, put them all in this giant list, and then we're just going to like chunk it into chunks and then say, okay, the first 100 is going to be one token, the next 100 is going to be another token, the next 100 is going to be another token. So it feels like there's probably some smarter, fancier way of doing that here, but this is a very early work. You know, it's kind of like they're not necessarily trying to be fancy here. The diffusion transformer that they trained for this one is based on GPT-2. We omit causal masking. So most transformers, right, that are trained for next token predictions, such as GPT-2, right, they have this masking that prevents them from kind of looking at the future. So here, you don't really care about that because you're generating the weights of a model, the parameters of a neural net. So you don't need to have this kind of masking. I just thought that was kind of like an interesting thing to think about there. You would do the same thing if you were using a diffusion model for images as well. Our decoders do not share weight. The global residual connection and conduct. Okay, that part was kind of annoying, so maybe we don't go into that. I think there's one interesting thing to look at here. So this is probably the coolest figure from this Peebles paper. So G.PT, which is this model, this diffusion model, which is a transformer that generates the weights of a multi-layer perceptron, which is used for classifying MNIST, right? So it's a little bit of a complicated concept to wrap your head around, but we're literally using a network to generate another network. So here, the network that is being generated is this multi-layer perceptron that does classification on MNIST, right? So this here is the loss surface of a MLP that classifies MNIST, right? So the blue parts here represent areas where the MLP produces high accuracy or low error, and the yellow parts represent a particular point in model parameter space where the MLP is shit, right? So maybe if you were to take a point right here in this yellow space, you would get a parameter, or you would get the parameters of a multi-layer perceptron that give you an accuracy of 42. If you were to take a point down here where the blue part is, you would get a model that produces an accuracy of 76. So basically think of the blue part as good models and this yellow part as bad models. And when you're doing gradient descent, you're basically initializing the network randomly. So you're starting in some random point here. And then what you're doing with SGD is you're basically going down the direction of the gradient, down, 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 and hopefully you end up in one of these like pits, all right? And this is much more high dimensional. So what they mean here by PCA directions is principal component analysis is a dimensionality reduction technique. So we can't actually visualize what the loss landscape looks like for a multi-layer perceptron, because a multi-layer perceptron, even for something like MNIST, has hundreds of neurons, right? Versus here, we only have 2 dimensions. We have the X and Y are the actual dimensions that represent the parameters, and the Z-axis is the loss landscape, right? So this is just a low-dimensional projection of a much higher dimensional situation. So it's weird to think about, but the same kind of like traversing down this hill and going into this minima is happening in a much higher dimension. It's just that as humans, we have a very hard time visualizing anything above 3 dimensions. So that's why we're using a PCA here. But I guess I'm getting kind of overly verbose here, but the dots are sampled from G.PT when prompted for low test error. So if you remember G.PT or Peebles' paper, it's not just a diffusion model, it's a conditional diffusion model, right? So you're conditioning it on something. So the same way that stable diffusion, you're conditioning it on some piece of text. You're like, hey, I want to generate a sample from the image distribution, or Q of X, right? In Peebles' paper, you're sampling from Q of X, but there's a little bar there that's conditioned on something, and the conditioning in Peebles' paper is basically a loss. So you're saying, I want a model, I want the parameters of an MLP that classifies MNIST that has a low test error. Okay, so that's what you feed it. The diffusion model says like, all right, here you go. Here, you starting from noise, I'm going to just iteratively remove the stuff, and then eventually I'm going to give you a bunch of numbers which represent the parameters of an MLP that has low test error, as you described. Okay, and if we do that, right, we start with different seeds, so different MLP initialization. So you're basically, think of the seed whenever you're generating something with a stable diffusion. This is like different seeds. And the interesting thing here is look at where all of these end up. So basically, it's not like you're always ending up in the same place, right? It's not like what you're seeing here is that this diffusion model is generating model parameter configurations which basically visually appear to be in the correct areas, right? In these basically low points of this loss landscape. Samples diverse solutions that cover distinctive positive curvature regions of the error landscape, which is distinct positive curvature regions is a very fancy way of saying it is valid areas, right? So it's not like you're diffusing things and you're getting like models that are here and here and here and here. It's like it actually is giving you good models. And here are more examples of that. So you can see that it actually, sometimes it ends up in kind of not good local minima, but it does seem pretty good at finding. We don't really know if these are local or global minima, right? Because this is a PCA projection of a much higher dimensional situation, but it seems pretty good, you know? Visualize the test error landscape, correspond to different random initializations. The dots are sampled when prompted for low error. We visualize the surface. We show that GPT samples that construct accurately from 2-dimensional PCA encodings. The plot suggests that G.PT has learned a multimodal distribution over parameters even when given fixed inputs. Pretty crazy shit, if you ask me. doxed. Hoopo is not a real hacker. I'm not a hacker. I've never done any like hacking in the sense of like trying to enter someone's computer or trying to like maliciously steal things from people's computer. That's not the type of stuff that I'm into. Oh, the sweater. Okay, I got you. Yeah, only you're not a hacker if you're not wearing a sweater. Oh, here, look at this. I ended up in the perfectly. We cannot synthesize the entire parameters of large architectures, such as ResNet, VIT, and Comnext, mainly constrained by the limitation of the GPU memory. But I don't think this is necessarily entirely true, right? I think this has more to do with the fact that this is just a small research group and they're using a single NVIDIA A100, right? Because we know that you can do that, right? Like OpenAI's Sora is a video diffusion model, and they didn't tell us explicitly, but we're pretty sure that they trained an encoder decoder. We're pretty sure that Sora is a latent diffusion model. And if you think about the space of a 4K video, that's pretty high dimensional, right? So if OpenAI figured out how to encode, decode, and do a latent diffusion model for a minute-long 4K video, we can probably train a encoder, decoder, and a latent diffusion model for something that generates the model parameters of a small VIT, right? So this is promising to me because it means that, okay, we're getting good results with the little tiny things, but we need to try it on bigger things. But the problem with that is that now somebody with a bunch of GPU money to throw around has to bite the bullet and actually run the test. Like, can you actually generate the parameters of a VIT with a latent diffusion model in model parameter space? Because right now, the only papers that we have, which are proof of concepts, are kind of these small research groups, and they don't have the type of money and the amount of GPUs to actually run and train something like that. So they're basically doing it on these toy data sets like MNIST and CFAR, and they're basically generating the parameters of little tiny MLPs and CNNs, but I don't see anything that fundamentally prevents this from being done with much bigger models. It's just that no one's really trying. Okay. Is there anything interesting here? Number of original models, location of applying our approach. So here they're basically showing you K is the number of original models. So it's like basically think of it like the data set size. So if you have a data set size of 1, so imagine if you trained Stable Diffusion on just one image, that would be K equals 1 versus K equals 500. Imagine if you trained Stable Diffusion on 500 images. So that's just kind of giving you an idea of like the data set problem here, where it's like for images, we have literally probably trillions of images on the internet that you can scrape and use, but there isn't that many model checkpoints or like full trained models that you could train on. So these are very small data sets. They are using augmentation, right? So they do add noise to try to augment this data set, but still limited by that. They tried on different layers, so they're not even generating the full ResNet 18. They're generating different layers of it. So they basically take a pre-trained ResNet 18 and then try to generate just some of them. So layer 14 to 16, layer 16 to 18, that would represent, for example, 14 to 16 would be maybe here to here, right? So you would only generate the parameters of these two layers, right? And keep everything else frozen. Noise augmentation makes PDIF stronger. Adding noise on the latent representations is more important than on parameters. So obviously that makes sense, right? With such a tiny data set, you need to have some kind of augmentation. So it makes sense that if you add noise, you're going to get slightly better results. Synthesizing the deep layers can achieve better accuracy than generating shallow ones. Generating shallow layer parameters is more likely to accumulate errors during the forward propagation than generating the deep layer parameters. So here what they're saying is that when they're generating subsets, right? So they're generating not the full model parameters, but just small subsets of the layers. So maybe just 2 layers or 3 layers. They're basically saying that they have better results generating these than they have generating these. So that makes sense, right? If you try to basically keep everything frozen and only generate these low layers here, you're going to end up, it's a much harder problem, right? Because these low layers here, like they create the low level features that these high level layers over here are going to use to then ultimately classify, right? Because these are classification models. But if you fuck with these low layers here, it's going to be fucked all the way down to the top, right? So it makes sense that they're going to have better results by just kind of messing with these layers here rather than messing with the very early layers, which are kind of these more primitive, high frequency, kind of like texture type features, as opposed to at the very high level, these are much more abstract, high level features, which are probably easier. Like that, the distribution of high level features in this model parameter space is a probably much more tractable distribution than the distribution of model parameter weights that you're seeing all the way down here in the low level features. But everything that I just said is just me trying to like read the bones. Like really, this is just some black box situation, right? And their conclusion here that generating shallow layer parameters is worse than generating deep layer parameters is a empirical observation, not some kind of theoretical conclusion. Noise augmentation plays a crucial role in generating stable and high-performing models. What about synthesizing entire model parameters? So, right, most of this they just generated just small subsets, so either the very last layers of a VIT or specific layers in a ResNet 18, but they also tried generating entire parameters. Let me see, where was I? Yeah, so they're going to generate a MLP3, which is three multi-layer perceptron with 3 layers in between, right? So very small little MLP, which seems kind of pointless, right? Like a 3-layer MLP on CFAR 10 is effectively pointless. That has like 0 use, you know? But a 3-layer MLP that is a little nerf right here. This is a 1-layer, I guess this is 3-layer MLP right here. You have input, middle layer, and then the final layer. But a 3-layer MLP that is a nerf, that has a little bit more use, right? If you can conditionally generate the MLPs for nerfs, I could probably use that. But in the Peebles and then this other paper here, they're generating classification MLPs, which are kind of pointless. They're more just toy examples to show that it works as a proof of concept. So this is the tiny little full models that they're generating. But the important thing here, right, is that they're generating the full model, right? So they show that, okay, we can generate just specific layers of the model, but we can also generate the entire model itself. And that's kind of the important part of the entire model parameters. 3 random seeds and visualize the parameters. I guess here they're just showing you that they're different, right? Which is another way of showing you this, right? Where when you run this diffusion process, you're going to end up with different points in model parameter space, right? Different final answers. It's not like you're going to end up in the same place every time, which would be a bad sign, right? If every single one of these points was just all in the same place, what that would tell you is that your diffusion model largely just overfit and it's just generating the same image of a cat every single time, right? You want it to generate different cats every time. So the fact that it's generating different parameters for these little tiny 3-layer MLPs is a good sign. So PDIF does not just memorize the samples from the original model in the training set, which is important when your dataset size is 500, right? 500 dataset size, very prone to overfitting. Is there any difference among adding noise or fine-tuning the original models? I think the best way to answer this is with this plot right here. So similarity represents IOU over wrong prediction. So this is like a classification model. So roughly think about what am I trying to say? I think I got confused here. Similarity represents how similar the final answer is to so one little multi-layer perceptron to another multi-layer perceptron, right? So if you were to look at the little multi-layer perceptrons that you trained from scratch, they have a high amount of similarity, right? So they both started from different seeds and they use gradient descent to kind of like move into one of the little channels, but they all kind of ended up in the same place, right? So if you were to use gradient descent, you would kind of end up in the same little area in the loss landscape. And that's kind of what this high similarity is showing you here. But the important thing that they want you to see here is that this orange bar and then this pink bar. So the similarity between models that you diffused and those models that you diffused and each other, and those models that you diffused and the original models is not as high as between the original ones. So it's basically telling you that your diffusion model is not overfitting. It's not generating the same image of a cat every time. It seems like every single one of these little MLPs that is being generated is slightly different, which is what you would want. And here they have Teasney, which is another, it's kind of similar to PCA, right? If PCA is a low dimensionality reduction technique so that you can look at these plots here. Here's another dimensionality reduction technique that people use all the time called Teasney. And you can see here that original adding noise to the original, and then the PDiff, there seems to be a little bit of a difference. It's finding a slightly different, I guess, minimum, but the key point here is that the red is not the blue. That's really what they're trying to show you. The generated models almost memorize the original model when k equals 1. That seems pretty obvious, right? If you were to train a diffusion model with a single picture of a cat, the diffusion model would just generate that picture of a cat. Visualization of the parameter trajectories of PDiff. So a parameter trajectory is much like when you use gradient descent, right? You're basically moving along this loss landscape, but step by step by step, where each step is based on the gradient at that area, which you're calculating from your loss function and the fact that your entire model is differentiable. A diffusion model is also going to go step by step by step by step. But the step by step by step is now coming from basically this denoising model, which is removing noise or basically slightly adjusting the weights of that model. So what does that trajectory look like? And it looks a lot weirder, right? So if you look at the trajectories of gradient descent, especially gradient descents that have momentum terms, like atom is one that's very popular. The M in atom stands for momentum, right? So generally, when you take little training steps using atom, right, there's this momentum that means that it kind of has a hard time changing directions rapidly. It generally has like this concept of momentum, so it like moves towards the same area a little bit more consistently, right? So look at that kind of smooth trajectory in the loss landscape that you get from these gradient descent techniques that have this momentum concept in there. Versus here, the diffusion model doesn't have that momentum term in it, right? It's just basically kind of removing noise. So the trajectory that you get is a lot weirder. You see, it's like going here, and then it's like, nope, I'm going to suddenly go here, and then now I'm going here, now I'm going here, now I'm going here. So the mean of the original models, this is the models that you trained with gradient descent. They all kind of end up in this little local space here, and this is the trajectory of the diffusion models, and the triangles here is where they end up, and the blue is where they started. So this isn't necessarily a great look for this paper, because what it's kind of showing you is that they're kind of ending up in the same place, right? When I look at this, I look at, okay, all of the blue dots are further away from this red star than all these triangles here. So what it's telling me is that there's this kind of like, there's one big pit in the middle, and then you're basically all just like funneling down into this pit. But it's also very hard to say that because these are very low dimensional visualizations, and it's more complicated than that. So it could be the case that there's a bunch of little tiny pits over here, and that's where these are ending up, and then there's another pit here, and maybe the pit right here is actually better than the pit right here. So I don't know, but it's a little sketch. Okay. Is there anything I wanted to show here? Our approach could be viewed as learning a prior over network parameters, represented by the train diffusion model. So a prior over network parameters is just a fancy way of saying that they're trying to learn this, right? This Q of X, right? So a prior is basically your guess of a distribution, right? So for example, when people say, oh, I'm using a Gaussian prior, like what the fuck are they actually saying? What they're saying is that, okay, I have a distribution of things, which I don't know what it is, but I'm going to say most things are normal distributions. Therefore, I'm going to assume that the distribution that I want probably is also a Gaussian distribution or a normal distribution. Therefore, I'm gonna assume that the prior is a Gaussian, right? So the prior is like kind of like your guess, right? Your initial guess as to what the distribution is. So in this case, when they're saying our approach could be viewed as learning a prior, it's basically they're learning this distribution of network parameters, right? They're trying to find this magical distribution that if only you could just heuristically right that, you could basically just infinitely get high-performing model parameters from it, but you don't have it, so the best you can do is basically approximate it with a diffusion model, and then the diffusion model, if it's a conditional diffusion model, you can condition it and then sample from it, and eventually that sample should be valid, I guess. Okay. These methods mostly operate in the small-scale settings, while PDIF shows its effectiveness in real-world architectures. I thought this was also a little cheesy. You know, it just feels a little weird whenever they're talking about, like, we're real-world architectures. I'm like, is that really real-world? Like, is CFAR 10 classification with a 3-layer MLP, is that a real-world example? I don't know. It seems pretty toy to me, but okay. Neural networks have several popular learning paradigms: supervised, self-supervised. Diffusion models can be employed to generate high-performing and novel neural network parameters. Using diffusion steps for neural network parameter updates shows a potentially novel paradigm. I think that's the most cool part about this entire stream, right, is that this is an entirely different way of creating neural networks, right? You're basically using a diffusion model to generate them rather than kind of doing this gradient descent. We acknowledge that images and videos are signals of different natures from the parameters of a neural net, and this distinction must be handled with care. Even though diffusion models have achieved considerable success in image and video generation, their application to parameters remains relatively unexplored. These pose a series of challenges for neural network diffusion. We propose an initial approach to address some of these challenges. There are still unresolved challenges, including memory constraints for generating entire parameters of large architectures, the efficiency of structure designs, performance stability. There's a lot. This is like a brand new area, you know? So if some of you guys are thinking about what's a research project that I could work on, this is completely unexplored, right? And you got here some papers, but these papers are just little toy problems. And I think that, to me, I'd love to see this on something much more intense. I'd love to see this on the parameters of a language model, you know, and I'd love to see some of the improvements in tokenization, right? It seems like the way that they're taking these neural network parameters, and in both of these papers, they're basically just flattening it, including this one, including this Apple paper here, where they're creating this NeRFs. Like, they're just kind of like naively flattening these numbers into a vector. I think you could probably do something more clever, right? And you're going to have to do something more clever in order to feed in an entire language model, a giant LLM. You're going to have to figure out some way to tokenize that, right? Similar to the visual patches and stuff like that. And then the way that people modified those visual patches into space-time patches in order to tokenize an entire video and then generate a video using a diffusion transformer, which is how Sora works, and how Lumiere, which is Google's video generation model, also works, and how Stable Diffusion 3 probably also works, right? They're using diffusions they're using a transformer for the diffusion model. I think there's probably all kinds of interesting kind of improvements that could be made on the tokenization of how do you tokenize model parameters. Okay. Was there something interesting in the conclusion here? Oh, yeah, they did something interesting here. So in this one, they did a permutation augmentation, which I thought was kind of a cool idea. So one thing to think about is that in a multi-layer perceptron, right, you have these neural nets, or you have these little neurons. Those little neurons have parameters that are the weights and the biases. But whenever they're turning these neural networks, or these little MLPs, into a one-dimensional vector, they're kind of just flattening it arbitrarily, right? But the way that this works, it's like you could actually swap these two, right? You could swap this neuron with this neuron and just make sure that the connections work, and it would still be the same, right? So an interesting thing in this paper is that they realize that, and they're like, hey, wait a second. Rather than just using noise to augment our very small data set, because we don't have a lot of these trained models, what if we also basically have a translation invariance as a form of data augmentation, right? And this is something that comes straight out of images, right? So whenever you're training image models for anything, there's all kinds of different data augmentations that you can do. And one of the common image augmentations are basically these things like left, right flipping and cropping and like cutting and sliding, right? So all of those are basically leveraging the fact that an image of a cat with the cat here is the same as an image of a cat with the cat here, right? Where basically those types of transformations don't mess with the fact that this is still an image of a cat. So there's a similar kind of thing here where in model parameter space, there's probably a whole bunch of data augmentations that you could be using to augment these data sets, right? In this one, they're just adding noise. In this one, they come up with a clever idea of permuting the kind of the ordering of these weights and biases in these vectors when they're flattening them. But I feel like this is just the beginning of the iceberg, right? I bet you that the same way that over 10 years, people figured out hundreds of different augmentations for images, there's probably hundreds of different augmentations you could do for neural network parameters, right? And in this space, in this research area where we're dealing with these tiny data sets of just 500 trained models, if we could have very, very good augmentation techniques to make that even more, that could lead to a lot of good results. So I thought that was a clever idea. Okay. Relatively simple data sets of neural networks with static optimizer hyperparameters. Yeah, so much like the other paper that we were looking at, this one's also kind of just limited to toy problems like MNIST classification with a 3-layer MLP. Okay. I think most of this other stuff is not necessarily super important, but I kind of want to go into like what is the limit of this, right? And where I'm going to start with in this rant is this paper here. So we had a stream, I think it was a couple weeks ago at this point, where we looked at quantization and sparsification, right? So we were looking at different techniques that people use to basically reduce the size of a model, right? So in this one, it's called quantization. Quantization is this idea where you basically reduce the data type of these model weights to much lower dimensional data types that basically are just 1 bit as opposed to like 8-bit, 16-bit, whatever you want. And then there's this other paper that we were looking at where this is more of a sparsification type paper where they're basically reducing the total number of weights by doing this kind of clever matrix multiplication, but largely just saying, hey, there's a bunch of parameters in this neural net that we don't actually need, right? So quantization is more like reducing the individual size of individual neurons, but sparsification or pruning is like removing a bunch of neurons. And to me, I think there's a combination of these two things, right? I think if you look at this paper, which I reference all the time, this is an old paper called the lottery ticket hypothesis. And in this paper, they found that neural network pruning techniques, right, where pruning techniques is this idea of like, hey, I can remove a bunch of these, right, can reduce the parameter counts of a trained network by over 90% without compromising accuracy. So what does that mean? It means that they present this hypothesis. There is a dense, randomly initialized feed-forward network that contains subnetworks that when trained in isolation reach the test accuracy comparable to the original network in a similar number of iterations. Okay, so where are you going with this, Hugo? What do you mean? Okay, well, if we cannot synthesize the entire parameters of large architectures such as ResNets, VITs, GPTs, LLMs, like those things have so many parameters, it's going to be very, very difficult to basically generate them in one shot like that with a diffusion model. But what if we're not generating full neural networks and we're generating extremely sparse, extremely quantized versions of these LLMs and big parameter models? And that's where I feel like there's a huge potential like merging here, right? Where, hey, if diffusion is going to be difficult because of just the sheer parameter count of these models, what if instead of using dense multi-layer perceptrons and dense versions of these VITs, and that's what you're actually figuring out how to encode and then figuring out how to generate with this diffusion model? What if you're doing that instead with these extremely sparse, extremely quantized neural nets, right? Could you end up with a diffusion model that generates the parameters of very powerful neural nets, except those neural nets are just basically super quantized, sparse versions of a larger architecture? I don't know. I just thought there was something cool there, but I'm just kind of hypothesizing. All right. Damn, you guys are popping off here. Let me see. I'm trying to see, scrolling through the chat here. Just watch your Mamba video. Great video. I appreciate it. Byte Cloud, big AI YouTuber. Who is ByCloud? I'm not cool enough to know what that is. If we could find the signal, turbo interesting. All right. Doesn't seem like there's any questions. Where are we at? 11:29. We're only an hour and a half, but this is also just like a one paper stream. I feel like previous streams I was trying to do a lot of different papers at once. Here, this one mainly we just focused on one paper, and I just kind of like had other papers that were related, but we basically went through the whole thing. So how about this? How about I sip some water, sip some coffee, pause for a second. I'll summarize this for you guys, but if you have any questions, type them in the chat. I'll answer your questions. I'm out of coffee. Oh no. Look at that sad face. No more coffee. So for context, this image here was generated with DALL-E 3. A lot of the original thumbnails were generated with, I think I used Stable Diffusion initially, then I used Midjourney, and then the most recent one I use is DALL-E 3. But I don't know, maybe I'll move to something new. You know, DALL-E 3 seems pretty good, but is this pruning going against the over-parameterization approach, meaning why it works generally? So these pruning techniques are post-training. So both of these, whether it's quantization or this type of sparsification or pruning, sparsification is like the kind of like larger umbrella term, and then pruning is a type of sparsification, but they're post-training. So in this case, you already have the trained model, and then you're basically sparsifying it post hoc, so after you train it, right? But what I'm saying is that this is a very involved process, right? You're literally doing this huge training process to get to a final point, and then you're running this sparsification process to basically reduce it into a smaller model, right? But another way to think about it is that there existed a small model there. There was already one there. It's just you just needed to find it, right? And the way that we find it right now is with this very kind of brute force, like taking tiny steps in this lost landscape until we end up at a point, and then sparsifying that, right? So that's kind of why I wanted to introduce this paper, where it's like the way to think about it is that the network is already there, right? It was already there. It's just you just need to find it, right? So maybe that's kind of what I'm saying here is that rather than doing this complicated process of like pre-training and then sparsifying it, right? As they mentioned here, this process does not need to be, you don't need to have basically a differentiable situation in order to do this type of diffusion, right? Like imagine if you had a data set of just, here's a bunch of sparse models, train an encoder decoder that figures that out, and then train a diffusion model that just generates sparse models for me, right? So is there some distribution of lottery tickets that we can effectively learn with this diffusion model? That's the question that I'm posing. And my hypothesis is that yes, there is. If we could only just get a data set of these very, very sparse language models, right, then we could train a diffusion model that generates sparse language models. And the benefit of that is that it generates sparse language models. You no longer need to go through this huge long training process to get to a sparse language model, right? Now you would just be able to generate one directly. But the problem there is that, okay, well, now how do you get that data set of sparse diffusion models, right? Or sparse language models? It's kind of like there's a chicken and egg problem here, where it's like, in order to create a diffusion model that generates a thing, you need to have a bunch of examples of that thing. So like, if you already have a bunch of language models, what's the point of getting a diffusion model that creates language models, right? It's like, don't you already have a bunch of those language models? So I don't know. It's kind of a chicken and egg, but that'd be really badass if you could generate language models, very sparse language models, just like that. ByteCloud is a dude who does a lot of clean AI, mostly image and video generation, over 100K subs on YouTube. All right. Sounds badass. I think we can retain and just see it in a different way. Okay. All right. Let me summarize this. Okay. Here's the summary, guys. So today, we went into a little corner of the machine learning world, a little novel area of the AI research landscape, right? Called the neural network diffusion research area. Or you could think of it as, another way to call it is generative models of neural network checkpoints. Or another way to call it is generating a weight space diffusion, right? So all of those are basically referring to this same concept, which is, can we train a diffusion model to generate a neural network directly, right? And even just the fact that there's like 3 different names for this kind of stuff tells you that it's that early, right? It's that early, it's that new, that there isn't like a single name for it, right? If there was like a if all 3 of these papers use the same terminology to describe this, it would tell you that it's a little bit more mature. But the fact that you have 3 different papers with 3 different names for what is effectively the same thing tells you that we're still very early on in this process. And we're also very early on in this process because the kind of 2 papers here, 2022 and 2024, they're doing this in a very simplified space, right? They're not generating the parameters of a 7B language model, right? What they're doing is they're generating the parameters of these tiny little multi-layer perceptrons that are used for classification on MNIST and CFAR, right? So these are basically toy problems that they're using as kind of a proof of concept that this entire technique even works. So the first paper that we looked at trains a latent diffusion model, where a latent diffusion model is a diffusion model that iteratively denoises a latent, which is effectively a compressed version of the original data itself. So the original data in this case would be the parameters of a little tiny multi-layer perceptron, and you are going to have to train your encoder decoder from scratch. The way that they're doing that is they're starting from a very small data set of just 500 examples, basically, as the most. 500 trained neural networks that have been trained with gradient descent. You're adding noise to those, adding noise to the latents, and you train an encoder decoder. Once you have this encoder decoder, you can then encode your entire data set, and that's what this latent representation here is, and then train your diffusion model as you will, right, by adding noise and then predicting that noise and so on, and then running that over and over again on all your different encoded neural nets, trained neural nets. And then once you do that, now you have a trained encoder, a trained decoder, and a trained LDM. Now you can just feed random noise into this LDM, which is frozen, and then whatever comes out of that, there's going to be a bunch of different denoising steps. Denoising steps, you're going to feed what comes out of that into this decoder, and then lo and behold, you're going to get basically this. You're going to get new and novel little models, right? New little multi-layer perceptrons that classify MNIST, right? And in both of these papers, this one is a little bit different. So this is a little bit older, and this is by William Peebles, which is our new. If Tim Detmers is the quant god, I'm going to now start calling William Peebles the diffusion god. So Peebles is diff god. Tim Detmers is quant god. Okay, so in diff god's paper, he basically does the same thing, except it's not a latent diffusion model. This is a diffusion model that operates directly in model parameter space, and it's also a conditional diffusion model. So it's a diffusion model that's not just starting from some random noise and then generating the models of a multi-layer perceptron. It's generating the parameters of a multi-layer perceptron conditioned on, in this case, a loss, right? So the loss is, you can think of it basically just like a number, which represents how good the model parameters were here, right? And they have a little bit of a bigger data set because they're basically saving checkpoints. So as they're training this model, right, the loss is going down, but they're saving a bunch of checkpoints. So as they're training this model, they're saving a checkpoint here and 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 here. And they're training this conditional diffusion model, which in this case, they use a transformer. So this one is a little bit better. This one is a diffusion transformer, which I think is a cooler, more modern diffusion model versus in this one, this latent diffusion model here is a one-dimensional convnet, which is a little bit sketch. Let me see if I can find it. Yeah, it's a 4-layer 1D convnet-based encoder and decoder, and the latent diffusion model as well. So a little bit more primitive, but of course the diff god is going to have a better diffusion model because he's the diff god. So, but the more important thing is that this data set is a little bit more filled out, right? And they also have a cooler type of augmentation. So here, because these are little MLPs, they permute the order of the weights and biases parameters in the one-dimensional flattening of the model parameters. And by doing that, they get a little bit better data augmentation that they do here, because here they basically only have noise as the form of data augmentation. And yeah, and then they get this conditional diffusion model, which you can basically give it a loss, and you're basically saying, hey, I want the model parameters of a multi-layer perceptron that would produce a loss of 0.02. And then your little diffusion transformer is going to be like, all right, here you go, boom, 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 boom. And it's going to give you these specific set of model parameters, or another way to think about it is a specific point in model parameter space. This is a low-dimensional PCA visualization of model parameter space with your loss landscape or loss manifold. And you can see how this diffusion model, when you query it with, I guess, a loss of 0 or something like that, and then different starting seeds, you end up getting a bunch of MLPs represented by each of these green dots represents one MLP. You can see that they're definitely in the right areas, right? So they're definitely kind of in the areas of low loss, and they're also in different areas, right? So that's another important point, is that they are kind of all over the place in a good way, right? You wouldn't want your diffusion model to just output the same little MLP parameters every single time, right? Because then it would tell you that you overfit to your very small data set. So that's basically these two papers, and it's promising stuff. So the main negative of both of these papers is that these are toy problems, right? They're generating these little tiny multi-layer perceptrons that are used for classification on these little tiny data sets. They do generate, for example, the last 2 layers of a VIT, but does that really count? Like, what's the point of generating the last 2 layers of a VIT for classification? It's like, it seems a little toy, right? The way that they kind of argue it is that, like, hey, I mean, it's a lot of parameters. We don't got that kind of money. You know, we're just a small little mom and pop research shop where you're just using one A100 GPU. Therefore, that's why we're using these toy problems. But an interesting thing that I found is that, hey, actually, maybe you could use it for something else, right? One actual production use case of very small, tiny models is NeRFs. In a NeRF, which people do use for modern kind of generative 3D stuff, even if Gaussian splats are a little bit better, a NeRF is a little tiny multi-layer perceptron. Okay, well now we have a use for this, right? And this is a paper by Apple where they basically are doing the same thing. They're diffusing in model parameter space, but this one feels a little bit more tangible because the models, the little multi-layer perceptrons that they're creating are these little NeRFs, right? So I thought this was a little bit more, it makes it a little bit more tangible, right? I think that when you're generating MNIST classifiers, it just feels like abstract, but this one, you're generating these little NeRFs that you could then use to create these meshes, and I just thought it was a cool way to kind of see exactly how the model emerges from the noise. In this case, there's a couple steps here, right? Because you're generating the parameters of an MLP, and then that MLP is then queried over a bunch of points in order to create a mesh, which you use a marching cubes to create. But this to me is just a very, very visual nice visual example of kind of what is exactly happening as you're denoising in this MLP space, versus this is a little bit more abstract, right? It's like, I don't really know what the fuck I'm looking at here. It's basically the parameters of an MLP or the parameters of a ResNet 18. And yeah, you're getting better accuracy, but like, okay, like what am I looking at here? Just like a random grid of noise. It looks like noise here and it looks like noise here, right? It's difficult to see that, but I thought this was a nice little visualization and something a little bit more concrete. Here's ResNet 18, or this is a ResNet 50, so a ResNet 18 is basically just a smaller version of this. So those were the two papers that we reviewed, and then at the very end, I kind of wanted to maybe hypothesize and do a little bit of like future, what is the right word there? Futurism? I don't know. Thinking about how does this look like in the future, and one thing I thought of is that, hey, we know that you can take these models that are very big and quantize them and sparsify them and prune them so that they're very small. So if we have proof that diffusion in model parameter space works, as long as your model parameter space is quite small, then maybe we should be figuring out how to create a data set of very sparse, pruned, tiny little models and train a diffusion model that generates heavily quantized, heavily pruned LLMs, right? So let's make a diffusion model that directly generates these winning lottery tickets, which would be pretty badass, right? Because then it would mean that we don't need to do this long training, right? We don't need to give $7 trillion to Sam Altman for him to basically create a Saudi NVIDIA so that we can do this blue curve here, right? The reason that Sam Altman needs $7 trillion to create the Saudi NVIDIA is so that we can do this blue curve here, right? So that we can literally just take little tiny steps in this lost landscape to eventually find our way into this little pit, right? And the more GPUs you have, the more you can take little steps and 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 end up there, right? And it would be a hell of a lot cheaper and a hell of a lot cooler if we basically had a model that just boom, got us to that final point just like that. Still a lot of things to solve, still a lot of problems. Maybe it doesn't even work. You know, tokenization of a model parameters, still completely unexplored IMO. Whether this thing even scales, still completely unexplored. But maybe that's where you guys can contribute. Maybe that's how you guys contribute to humanity, is by figuring out how to do this. That's all I got for you guys. Completely truss out pre-training and GPUs. Yeah, potential. All right. Based diff god. All right, that's all I got. I don't see any questions here. So hopefully you guys got something out of that. Hopefully I piqued your interest. If not, I'm sorry, you know. Maybe join us for tomorrow's stream. So tomorrow, it's a different type of stuff. We're going to be looking at long rope. So long rope is the positional encoding or embeddings. Basically, these little pieces of information that you add to the sequences that you're feeding into a transformer, whether it's a sequence of visual patches or a sequence of text tokens, right? You're adding this positional information to it. And rope became popular, and now there is long rope, which basically allows for a much longer context. And last week, I predicted that the Gemini 1.5 context length, the way that they were able to basically 10x that is via ring attention, but it could also be this. So after I kind of reviewed this paper a little bit, I'm like, okay, maybe it's this as well. So TBD, of course, Google's a little bit closed AI, you know, OpenAI is certainly not going to tell you what the fuck they're doing to get bigger context, but this could be the Gemini 1.5, the reason Gemini 1.5 can do 10x the amount of contacts. We don't know for sure, but I don't know, maybe after we read it tomorrow, we figure it out. So if you're interested in that kind of stuff, join us tomorrow. If not, have a great weekend and have a good day. Thanks, Aries, Majetti, Spyro, Victor, who else? Raphael, Timothy, Joseph, ByCloud, English, Emily, Darshan, Ed, 2ARX, Ed again, Heliophobic Dude, Nikhil, and Sagar. Thanks, everybody. Hope you guys had a great time, and see you guys tomorrow.